All right. Good afternoon, everyone. Hope you all had a good Labor Day weekend. Feels like a Monday squared, I think, to me. All right, so we are continuing what we started last time, which was 1.6 out of the textbook. That section has to do with limits involving infinity. And so what I wanted to remind you of is one of the main ideas from what we did discuss about this section, which was anytime we're taking a limit, so I'll say here, in the limit, that's kind of the verbiage I use, or that's the verbiage we use when we're talking about when we're taking a limit of something, we're in the limit, okay? So in the limit, when you're doing something in the limit, and you get something like this where you have the numerator of the expression is fixed, and it doesn't matter if it's positive or negative, does not matter. If the bottom is going to infinity, then the expression is going to be headed to 0. And we can actually add to this plus or minus infinity. It doesn't matter on the bottom either. If it's getting big negative or big positive, this ratio heads towards 0. And I showed you graphs and tried to convince you of this. So what we'd like to do now is see how we can use this very important property of limits to solve some more challenging limits. So we're now going to kind of shift our attention away from this idea of fixed over infinity and now look at one of our other indeterminate forms, which were on the sheets that I gave you, the limit summary. We have spent time on 0 over 0. We've done that already. Algebra trick, right? That's what we do. Today, we're going to start looking at what happens when you get infinity over infinity. All right. So here we go. So I'm going to just throw an example out here. So what if we take the limit as x goes to infinity of 3x plus 1, let's say over x squared plus 4. All right, so again, the idea here is that x is getting really, really big, right? X is going to infinity, it's getting really, really big, and it is positive, right? Positive big number. So we start looking at what happens here. So 3 times a huge number will still be a huge number, and if we add 1 to it, it'll still be huge. So the numerator is becoming infinitely large. And the denominator is also becoming infinitely large, because when we take a huge number and square it, it's going to still be huge, right? Get bigger actually. And then we add 4, that's still big. So we get infinity divided by infinity. Now this is not 1, right? This is not 1, just like 0 over 0 wasn't 1. This is basically bad, okay? And that means we need to do some algebra or some trick, okay? Now, when we had 0 over 0, we were doing things like factoring, we were doing conjugates, we were doing, if we were dealing with fractions, we were getting common denominators. So we did a lot of algebra that kind of tied into algebra. When you took college algebra, we were doing a lot of that algebra, right? But for problems like this, when you see infinity over infinity, we're still going to do algebra, but it's going to be different than what we've been doing. It's not going to be factoring. So watch what I do, okay? Watch what I do, and then we'll talk about why I'm going to do it, all right? So in a problem like this, what I do is I focus my attention on the denominator, and I look at the highest power of x that I see. I see an x squared there, okay? So what I'm going to do now is I'm going to take this limit, and let me write the 3x plus 1 out here. I'm going to leave a little space in front of it on purpose here. I'm going to multiply by 1, okay? So I'm going to multiply by something over itself. And the thing that I'm going to put out here is this, 1 over x squared over 1 over x squared. Now, the reason I'm using x squared is because I saw the highest power in the denominator was x squared. That's why I'm using x squared here, but I'm doing 1 over x squared divided by 1 over x squared again. So this is 1, so I'm not changing the problem, I'm just making it look different. And now I'm just going to do algebra and distribute it through. Okay, so I'm distribute here, and then here, and here. So I trust that you can do this algebra. Let's just go through it here. We'll have, let's see, when we multiply 1 over x squared times 3x, we'll get 3x over x squared, right? And then one of the x's will cancel, so we'll get 3 over x. All right, that's what we get on that first multiplication. And then plus, now the 1 over x squared times 1, and I get another 1 over x squared. And then on the bottom, 1 over x squared times x squared gives me a 1. And that's very important, all right? You'll see in a minute why. That's a 1. And then plus the 4 times 1 over x squared, which will give you 4 over x squared. Any questions on where any of that came from, or like how I did any of the multiplication? Okay, now going back to what we talked about last time in this main idea coming in today, if we ever take a limit and we have a number on top that's fixed and the denominator becomes infinitely big, this will go to 0, won't it? So if I take a limit right now and I look at these separately, this by itself, this by itself, this by itself, each of those 3 expressions are fixed numbers divided by x, and x is getting big, right? So this, all 3 of those should vanish, right? They should all go to 0 as x gets bigger. So I'm going to just say that goes to 0, that goes to 0, that goes to 0, right? And so what I'm left with is, and I'm not going to write the limit anymore because I've now let x go to infinity. I'm going to write what I got on top, 0 plus 0. And on the bottom, I got 1 plus 0. And so I get 0 over 1, and that's okay. 0 divided by 1 is just 0. So the limit as x goes to infinity of this expression is 0. Any questions on how I did that? I'm going to talk about why I looked at the x squared in a second, but I just want to make sure everyone's okay with this.
So we're basically, what we need to do is get to 0 instead of infinity over infinity.
You need to get to, well, it's not, you're not trying, the answer is not always going to be 0. If the answer was always 0, then I would just tell you anytime you see infinity over infinity, your answer is 0, but that's not the case. What we're trying to do in these is come through with something that is going to, let's say, let me explain this. I want to show you the picture first before I wanted to try and see if I could get you to tell me why I use 1 over x squared, but let me do this first. 3x plus 1 over x squared plus 4. Okay, so here's the graph. And as we go to infinity, that means we go out the x-axis, right, in the positive direction. Notice that this graph is approaching 0, isn't it? And that's what we were able to just determine using that little thing I did, right? We were able to figure out that that's what's happening. Now, can anybody tell me why using the 1 over x squared here, why looking at the denominator's highest power and doing this, why that is a useful thing? Can you tell why I did that? What did this green term turn into?
1.
1, right? And what that means is that if this x squared, right, if the x squared was the highest power of x that I saw, then if I come in with a 1 over x squared, what can you tell me is going to happen to anything else that would have been down here if x squared is the highest power? What would all of those do when I take the limit? What did the 4 do?
It turned into 0.
It's going to go to 0, right? Because x squared is the highest power down there. So definitely it's going to be higher power than the 4. So this thing should go to 0. What if that had been, let's just say, what if that had been 4x, right? Let's just say it was 4x. The highest power is still x squared, right? So this would have been 4x. And then what would this term have been instead of 4 over x squared?
Is
4 over x.
4 over x. But you know what? That's still going to go to 0, right? As long as I come through with the highest power that I see on the bottom, then I'm guaranteeing that I'm going to have a number in the bottom. The rest of them will be zeros. And having a number on the bottom keeps us from getting division by 0. Does that make sense at all? I mean, I'm trying to get you to see why we're doing it. If you don't see the why, then you can just do it. But I think the why is important. So let's do another one. Let's do another one. How about this one? Limit x goes to infinity, 3x minus 1 over x squared minus 4. I changed the problem just slightly. Do y'all see the difference?
It's negatives.
I put, yeah, you know what?
Subtracting instead of adding.
Let's make the bottom minus 4x. Change that to minus 4x.
So I have a quick question.
Yes.
What would you have done if your highest like possible number was on top?
You always look at the denominator.
Okay, so it doesn't matter. You look at that. You're looking for the highest number in the denominator.
In denominator, we'll do one. We'll do one in a minute here.
Okay.
I'll pick something on top that's bigger, and you'll see what'll happen. Okay, so for this one, again, let x go to infinity. So 3 times infinity is a huge number. If I take 1 away from that, it's still huge, right? So the numerator goes to infinity. Now, the denominator is a little bit tricky because of the minus. So think about this, because it's not obvious. I have a number that's getting big, right, squared. So this by itself is headed to infinity. Y'all agree? But then I'm subtracting from that this 4 times a huge number, right? 4 times a huge number, that's going to be a huge number. That's going to be infinitely big also, right? And infinity minus infinity is not 0. Again, this is an idea. We're saying this number is really big and we're subtracting a really big number. That's not 0. So we have to think about this a little bit, because just generally speaking, we don't really know what this answer is. But you can convince yourself of what it is if you just think about the powers. X squared, right? If you square a number, won't that be bigger than multiplying it times 4? If the number's big, right? If the number's really big, this is true. So like, let's say we take 1,000,000. 1,000,000 squared is definitely bigger than 4 times 1,000,000. Do you agree? So the x squared dominates the 4x because it's a higher power. So what that allows me to conclude from this is that this is going to be infinite, because I'm taking a huge, huge, huge number and I'm subtracting a huge number, but not quite as big. Okay. And so I should get a positive number there. Do you agree? Like some positive big number. So my denominator is also infinite.
Wouldn't it have the number have to, or whatever infinity number have to be like, I don't know, greater than 2 or something like that?
Yes,
If
yes.
you threw
I mean,
1 in there,
yeah.
it would.
We could figure out, like, if it's, I mean, obviously if it's 1, right? If x is 1, then that's not true, right? But the key is that we're letting x get huge. And so, yes, it may not be true for the first few values of x, but eventually, right? Eventually, way out there, the x squared is going to dominate the 4x. Okay, so I have infinity over infinity, and so I'm going to sit here and look at the highest power of x, and I'm going to do the same thing. 1 over x squared, 1 over x squared, and then I distribute through. So we just did this a second ago, so we're going to get 3 over x squared. I'm sorry, 3 over x minus 1 over x squared over 1 minus 4 over x. just distributing everything through, and I already simplified, cleaned everything up. And all the stuff that's fixed over X, all of those are going to vanish to 0. And so we should get 0 over 1 again, which is 0. Now, the answer is, like I said, the answer is not always 0, or else I would have just told you that from the very beginning. But the 2 examples I've given you so far, we've had 0. We could convince ourselves, I'll just graph it. So here's the graph of this one. And you can see, yeah, like see in the like when X is small, things aren't happening the way that we're saying they're happening. But when X gets big and you go out this way, you can see it's approaching 0. Is this all clear? All right. So what about this? Limit X approaches infinity. 3x cubed minus 4x squared plus, let's go minus x, minus 10, all over 5x cubed plus 27x.
3/5.
3/5, right? So you know that probably from college algebra, right? Or no? So yeah, we'll get to that. This in college algebra, you're probably taught how to do this by, if these powers are the same, that you just look at the numbers out front. So, you know, what we're actually doing here is finding a horizontal asymptote of the function. That's what we're doing. So we do have a shortcut for this, okay? But I don't want to talk about it yet because I want you to see where that shortcut comes from. So here, we first have to convince ourselves, again, that we have infinity over infinity. So this goes to infinity, minus that goes to infinity, minus that goes to infinity, and minus 10. So what do you think? Do you think this 3x cubed, as x gets really big, will it dominate over the x squared and the x? Eventually, right? I mean, like, if I let x get big enough, then these are insignificant. You have to kind of wrap your head around that idea. Cubing a number, a big number, is going to give you a much bigger number than squaring a number. For big numbers, right? For big numbers. So eventually this thing, as x goes to infinity, this numerator will become infinite, positive, infinite. And the denominator, I think this one's easier because I put a plus between them. So infinity plus infinity, you get infinity. We identify the highest power of x on the bottom, x cubed. And so I'll multiply by 1 over x cubed over 1 over x cubed. This will guarantee me that when I pass it through the denominator, I'm guaranteed going to have a number on the bottom because that x cubed is going to cancel. So let's see what we get. So distribute, boom, 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 boom. We should get 3 minus 4 over x minus 1 over x squared minus 10 over x cubed. On the bottom, we should get 5 plus 27 over x squared. So I'm not showing that there's x's that cancel and things like that. Is everyone okay with that? Any questions here? And now everything with a constant on top and an x on the bottom, all of those will vanish, right? And this is the first time this has happened. We're actually left with a number on top, aren't we? We're left with 3. And on the bottom, we're left with the 5. And so your answer is 3/5. Daniel, was that you that said that? Somebody said 3/5 in the very beginning. I'm not sure who did it. No.
I think it was Daniel.
Yeah. So in college algebra, you're taught that if you're ever looking at a rational function, this is important, it had to be a rational function, a polynomial divided by a polynomial, then if you wanted to know where the horizontal asymptotes were, what you'd do is you would look at the degree of the numerator and denominator and compare them. And if the degrees were the same, then you were told that the horizontal asymptote would be the leading coefficients. If you remember that, great. If you don't worry about it. But do y'all see why that's the case? If these two right here, those powers of x, if those are the same, right? If the highest power of x's are the same on the top and bottom, then when you come in with that 1 over x cubed, 1 over x cubed on top and bottom, those leading coefficients are going to stay there, right? That 3 is going to stay and the 5 is going to stay. Everything else is going to go away. And so that's why in college algebra, you're told just, oh, if they have the same degree, just look at the leading coefficients. Does anyone remember in college algebra what you were told if the degree of the bottom was bigger than the top? What the horizontal asymptote was?
0.
0. 0. Do you see why? If the degree on the bottom is bigger than the degree on top, then what are you going to come in with on the outside?
The one on the bottom.
Yeah, the one on bottom. So when you do that through here, right, you're going to be left with a number here, but what's going to happen up top?
All going to turn 0.
All of them go to 0, right? Because the highest power of x is down here on the bottom. So it's going to kill everything on top, which means your answer is going to be 0, and that's why, right? Does anyone remember what you got in college algebra when the degree of the numerator was bigger than the denominator?
Wouldn't you have to do that some kind of division? I can't remember what it's called.
Yeah, you'd find like
division?
slant asymptotes, right? Like you'd find like a slant asymptote. Not
Yeah,
every
the
college
horizontal
algebra-
asymptotes, whatever. Yeah.
Yeah, not every college algebra class goes through those. But basically, if the degree of the top is bigger than the bottom, then you would have no horizontal asymptote, which means it would not flatten out. We haven't looked at that yet, though. Let's look at one of those. That's, I think, Hunter brought that up a minute ago. What happens if the top's bigger, right? So let's try it. So what happens if your degree on top, let's go with, I'll just make one up, x cubed plus 1 over x squared plus x. Let's just do that. So first things first, let's just convince ourselves this is headed to infinity over infinity, right? So we're going to take the highest power we see on the bottom, which is x squared. And we're going to come in with 1 over x squared over 1 over x squared on the top and bottom. Now, what this is guaranteeing me is that once I do this, on the bottom, I'm going to get a number, right? The bottom is just going to be a number. But the numerator, because the power on top was higher, right? Then I'm going to have at least one piece that doesn't go away because the highest power is on top. Let's just see what happens. So we get limit, x goes to infinity, distribute, distribute. So we should get x plus 1 over x squared over, here comes the 1 right there. And then this one gives us just 1 over x squared, or 1 over x, I'm sorry. Fixed over x, those are going to vanish, right? The bottom is headed to 1, right? Or it is 1. But where's that numerator headed?
Infinity.
Infinity, right? Infinity over 1, which means it's headed to infinity. Which means it's not headed to a horizontal asymptote, right? It's not flattening out to something.
That means it's shooting off at probably a roughly 45-degree angle, just out.
Yep, it's headed out. Now let's go ahead, I'll graph it. X cubed plus 1 over, what was it, x squared what? Plus 1? Plus 4?
Plus x.
Plus x? There it is. So you can see here from the graph that as you go out to infinity, right, where's the graph headed? Off to infinity, right? Off to infinity. And so we were able to determine that. So you might want to ask you might be asking yourself, look, if we did this in college algebra and I didn't have to do any limits, right? All I had to do was inspect the degrees, then why do I have to do this, right? Why do we need to do this, right? I mean, I think that's a fair question. Well, I don't have to give you a polynomial function. So let's try something that's not a polynomial, like this. Okay, so whatever rules you learn in college algebra about comparing the degrees, all that stuff, can't use it here. This is not a rational function. It's not a polynomial divided by a polynomial. So that means you can't use that. So you have to do something else, which is what I've been showing you here today. So first, the numerator's headed to infinity, denominator's headed to infinity. Are we okay with that? Okay, so now the tricky part. I'm supposed to look at the highest power of x in the denominator, right? Which is x squared. And then I'm supposed to come out here and I'm supposed to multiply the top and bottom by 1 over something, right? No, be careful here. Because think about what you need. You need whatever you multiply by to turn that x squared into a 1, right? To kill off that x squared. So I'm not going to use x squared out here. I'm not. It's because there's a square root here, right? So, Maddie, you look like you want to say something. No.
Would you do 1 over x?
1 over x. Maddie, I couldn't hear you if you were talking. Who's that? Ricardo? Did you say 1 over x? Was that you? So why 1 over x?
Because the root will cancel out the x squared to just do an x. So you do
How
1 over x.
How though? You're right, but I'm trying to help me explain it. Like
Oh,
why
okay.
1 over x out here? Why is that going to cancel that x squared?
Because radical x squared isn't that just x? So 1 over x times x, make it to 1.
Yes, I agree. Radical x squared is x, but you can't take, when it comes to a radical here, you can't do these individually, right? Like the square root of x squared plus x plus 1 is not equal to square root of x squared plus square root of x plus square root of 1. That's not the same, right? So you can't do this. You're not wrong. I want to make sure this is the point I want everyone to be aware of. I know that we've all seen this before, but maybe not in this way. Back when you were learning about radicals, you were told that if you had, of course, the square root of x squared, then that would be x, right? That's something we'd all kind of agree on. But if you had something like the square root of x cubed, then you could look at that as being the square root of x squared times x. And then that could be broken up into the square root of x squared times the square root of x. And then that turns into x root x. In other words, you're taught that if you see like x cubed, right? Then you can pull 2 of the x's out of the root, right? 2 of those x's come out of the root and wind up being a single x on the outside. So if you have a pair of x's inside the root, they come out of the root as an x. Let me say it again. If you have a pair of x's inside the root, they come out of the root as an x, right? Well, what would be the reverse of that? If you have an x on the outside of the root, and you want to push it into the root, what happens to it on its way in?
It would become x squared.
It becomes squared, right? Now that's important. If you ever want to push something into a root, a square root, it gets squared on its way in. I'll give you another example. If I wrote this down, 3 root 5. If I told you to put this 3 back under the root, you would have to push it into the root and become a 9, right? So this is square root of 45. Now, we never really did that. We never pushed things into roots. We always did it the other way around. But what I'm trying to get you to see here is that I need this x squared to go away. So I need a 1 over x squared on the inside, right? Which means I'm going to hit it with a 1 over x on the outside. And when it gets pushed into the root, it gets squared on its way in. You square 1 over x, you get 1 over x squared. That makes sense?
That was not what was, I was not thinking that, but like,
Okay, it
it
works.
makes a lot of sense. It does.
Okay.
I
Good.
get what you're saying. I'm trying to see how that's different than what I was saying earlier, because isn't that kind of the same thing? I'm kind of confused how it's different.
Well, all you said, what you said was that let's use 1 over x, because when you look at the square root of x squared, that's really kind of like an x. And so that's why we use this. Yes, I agree with that. I agree with that. I just wanted to be clear that you can't split it up into 3 separate terms. And I'm not saying this is what you were saying to do. I just want to make sure that that wasn't the intention of your statement, is that this becomes this, this, this. And now you're saying, oh, the highest power of x I see is 1. And that's why I'm using 1 over x. Algebraically, we can't do this. So yeah, I'm not disagreeing with you. I'm just trying to clarify that way it doesn't come across to maybe someone else in the class the wrong way. That's all. All right, let's try this. I'm gonna push this in now. Ready? Now on the top, it doesn't get squared, right? It doesn't get squared because there's no square root on top. So it just distributes through. We get 4 plus 1 over x. And now on the bottom, now watch. I'm going to take this in 2 steps. I'm going to push the 1 over x in, which makes it a 1 over x squared. But now it has to distribute through to everything that was in the root, right? So that's like me pushing this 3 in. I push the 3 in as a 9. I push the 1 over x in, it becomes a 1 over x squared, and then it has to distribute. So when I distribute, I get 1 plus 1 over x plus 1 over x squared. And now everything that has a constant over x goes away. When I take the limit, right, those go away. I'm left with a 4 on top over the square root of 1, which is just 4. Questions? No?
No questions, but could we do another example like this one?
Yes, I'll do another one.
Could we maybe use like a x cubed or something in the bottom of
I was gonna do that. So let's go limit x goes to infinity. Let's go x squared minus 5x plus 1 over, let's go square root of x to the 5th plus x plus 3. Okay, we get infinity over infinity, right?
So just, I want to try to speculate.
Okay,
Would we multiply this by 1 over x to the 3rd? If I
1 over
remember
x
how
to the
exponents work correctly?
3rd. So you want to do 1 over x to the 3rd on the outside? So
Yeah, I think I'm remembering exponents working like that, because that should give us x to the 5th once we push it in.
So when you push it in, it gets squared, right?
Yeah.
So if you took 1 over x cubed and squared it, then that's 1 over x cubed times 1 over x cubed. That's 1 over x to the 6th because you're
Yeah,
adding.
all right, I was misremembering.
Right? Okay, but I think with that, you might be able to figure out what it would
Yeah,
need. to be.
2.5, 1 over x to the
2.5.
2.5. Would that be a viable thing to do?
Absolutely.
All right,
Absolutely. Now, I'm not going to use a decimal. I'm going to use a fraction instead.
understandable.
I'm going to use 1 over x to the 5 halves. 1 over x to the 5 halves. Now, why again? Because I want the x to the 5th to cancel, right? I want that to go away. So I need to figure out, like, what do I square, right? What do I square to get x to the 5th? So I have to take 1 over x to the 5 halves. If I multiply that times itself, that's 1 over x to the, well, I add these up, right? 5 halves and 5 halves gives me 10 halves. And that would give me 5. Now that usually confuses people, okay? That usually confuses people. So I have another way you can do it that might be a little easier for you to wrap your head around. So another way you can do it is this. You could go 1 over the square root of x to the 5th. 1 over the square root of x to the 5th. Now, think about this. If you take that and square it, you square the top and bottom, right? When you square the 1, you get 1. But then when you square the square root goes away and you just get the x to the 5th, right? So, but these mean exactly the same thing, don't they? Doesn't the square root of x to the 5th mean x to the 5 halves? I mean, that's what rational exponents are, right? If you have the, the nth root of x to the m power is the same as x to the m over n. So I'm just writing it a different way. I personally, this is me personally, I like the top way, only because I'm going to have to put these together, right? So I'm going to stick with this. I'm going to show this one in detail. We're going to have x squared over x to the 5 halves minus 5x over x to the 5 halves plus 1 over x to the 5 halves over. Now, when I push this in, what does it become when it goes in?
X to the 5th.
1 over x to the 5th. And then that will get distributed through to these. So that'll get pushed through. So I'm going to cheat. I'm going to copy this. So I don't have to write it all again. So when I distribute through the bottom, I should just get 1 plus 1 over x to the 4th. These are easier to do, so I'm just going to write them out. 3 over x to the 5th. Any questions there? I'm going to circle the ones I know go to 0. That goes to 0 for sure. That goes to 0 for sure, because I have fixed over something that's going to infinity. The only two I need to kind of convince myself of are these two. So on the side here, I'm just going to remind myself x squared over x to the 5 halves is the same as x to the 2 minus 5 halves, which is x to the, I need a common denominator, so that gives me 4 halves minus 5 halves, which is x to the negative 1/2. Right? X to the negative 1/2. Which is the same as 1 over the square root of x. So this piece right here, is it going to go to 0 or not? Is this one going to 0 or not?
It would have to go to 0 because square root of infinity is still going to be infinity.
Yeah, so this right here is still a fixed number over something going to infinity, right? That's what that is. So that is still going to go to 0. And then we could do the other one a similar way. Go convince yourself over here that 5x over x to the 5 halves should be at 5x to the negative 3 halves, which is the same as 5 over the square root of x cubed, which again is fixed over infinity. So that one will go to 0. So at the end of all of this, I get a 0 on top and the square root of 1 on the bottom, which is just going to be 1. I'm sorry, 0. What do y'all think? I hope that one helped and didn't make it worse, Isabella. Is that all right?
Yeah, that helped a lot.
Okay,
Hey, quick question.
yes.
How do you get from 5x over x to the power of 5 over 2 to 5x to the power of negative 3 over 2?
I did, this is x to the 1, and then you subtract, so 1 take away 5 halves is the same as 2 over 2 minus 5 over 2, which is negative 3 over 2.
Right, gotcha.
Thank you for asking though.
Fractions are not my strong suit.
Look, you'll get better at them. You'll have no choice. It'll be, you know, one of those things is as you progress through calculus, your comfort level with fractions will become much better. I've always said that, like, your abilities in algebra, like your skills, your algebra skills, by the end of calculus 1 will be so much further along than they were when you finished algebra. And when you get done with Cal 1 and you're in Cal 2, your whole like fraction thing is going to be much smoother. I mean, we work with fractions all the time in this class. So this quick arithmetic, you'll get fast. It'll get better, I hope. Okay, so the moral of the story is if we see infinity over infinity, we're going to try and look at the highest power of x on the bottom. And we're going to try and see if there's some way we can multiply the top and bottom by something that'll turn that into a number, and then see what happens to everything else. That's it.
I have a
Okay.
quick question.
Mm-hmm.
So you get that square root of x cubed because you're taking the numerator of that like negative power and just kind of like flipping it almost.
This right here?
Like, yeah, either that
here,
or the
here.
other answer.
Yeah, this right here. This, I'm rewriting that as 1 over x to the 3 halves, dropping it down because negative exponent, I drop it down. And then there was a 5 in front, right? So I just put the 5 on top. So 5 over that. And then this, I just rewrote it in a different form using that formula right up here.
Okay, yeah.
Yeah. Okay, so infinity over infinity. So let's try something else. Let me see if I can't throw a curveball at you. I don't think this is going to get y'all, but oh no, sorry. So what do y'all think here?
Multiply by 1 over x over 1 over x.
Multiply by what?
X squared. 1 over x squared over 1 over x squared.
Because you see an x squared here,
Mhm.
right?
And
So-
also with that, we could get. Ooh. Never mind.
So don't forget, what's always the first thing we want to check?
if it actually goes to infinity over infinity.
Like what's happening, right? So if we get infinity over infinity, I'm on board with looking at the x squared. Okay, I'm totally on board with that. But I first want to make sure that it's infinity over infinity. Now, I know that the bottom is headed to infinity. That I agree with. Okay, but what about the top?
Wouldn't it just equal 5?
Well, as x goes to infinity, what does sine of x do? We talked about this last class.
It keeps fluctuating between 1 and -1.
That's right. So when we add 5 to that, it's just going to be, well, think about what that numerator is if I asked you to graph it. Wouldn't that be a sine function that you shift the whole thing up 5? That's all it would be, right? And so that's always going to be bounded, right? The numerator is bounded and the denominator is infinite. And I told you last class that when you see this, what? Bounded over infinity. Where's it going?
Isn't that 0?
It's 0.
0.
Okay, it's 0. And I pointed this out to you in class last time when I showed you the little cheat sheet that I give you all for this class on the formulas here, the limit summary. I said fixed plus or minus over infinity goes to 0. And on the bottom, remember I said here fixed means non-zero and or bounded. 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 Okay, so that's what I just used right there. The fact that is everyone clear on why the numerator is bounded? Like the biggest this could be would be 6, right? Do y'all agree the biggest this could ever be, the numerator would be 6? Sine of x is bound between -1 and 1, right? So the biggest this could ever be would be 1 plus 5, which is 6. The smallest it could ever be would be 4, right? -1 plus 5. So even though the numerator is fluctuating, it's bounded. And anytime you have something bounded divided by something that gets infinitely large, that's headed to 0. We'll graph it just for fun. So if we had sine, I know I showed you all this last time. I was talking about dampened oscillators. I don't remember what it was, x squared plus x. Whoa. I think that was it. So it's this green one. Wow, you can't even tell it's oscillating. Well, you can't even tell, but it's kind of like wiggling its way down. It's hard to see it, but it is wiggling its way. Maybe if let me change it. I'm going to put a times, maybe I can make it, I can like really kind of, yeah, there we go. I'm kind of forcing it here, changing the amplitude of that sine function, which is kind of changing the wiggle. So you can kind of see that wiggle a little more. See it pop back up a little bit and then go down. It's popping up again, but not as high. And then, I mean, it's getting funneled into 0. Okay. All right. So the moral of that one, don't get yourself like too like down one path. Always start every limit with what's happening, right? 0 over 0, bad, right? Algebra. Infinity over infinity, okay, yeah, algebra, but we'll look at the highest power. Fixed over infinity, that's 0, there's no work, okay? Bounded over infinity, there's no work. All right, here's a new one.
I guess it'd also be possible to just end up with your it approaching 0 over infinity, which is just what would that do?
0 over infinity. Yeah, that's a good question. What would happen if you took a limit and you got 0 over infinity? What do y'all think would happen?
It would equal 0.
It would head to 0. It would head to 0. Because the numerator, again, the numerator is trying to get small, right? The numerator is headed to 0, so it's like really small, getting smaller and smaller and smaller. And then you're taking that small number and dividing it by a huge number, which makes it even smaller. So it's kind of like they help each other out, right? It's like the numerator is like, hey, I want to be small. And the denominator is like, hey, I'm going to make you small. So we're working together. We're going to get small fast. That makes sense? So that would head to 0. Now, again, in the limit, okay, in the limit, this is what would happen. If I take 0 and divide it by any number other than 0, then the answer is 0. But Okay, how about this one? This one's not gonna, this one might seem too easy because it is easy, but it's gonna kind of introduce a new idea. All right, what do we got? So where's this headed? X squared,
To infinity.
infinity, okay, and then we take away from that infinity. And the x squared dominates the x, right? So this should just become infinite, positive infinity. I already kind of explained that to you, right? I want to show you how I can prove this to you a different way, right? Do you agree I could have taken this and factored an x out? Couldn't I do that? And if I do this, now this heads to infinity, right? But now I have multiplication times. Now where does this head to? Huge number, take away 1. Still huge, right? Still huge number. So this is headed to infinity. A huge positive number times a huge positive number should equal a huge positive number. So the answer is infinity here. So two different ways of doing the same problem, right? This way was just inspecting and saying, oh, x squared dominates x. So it's going to be this. Here we actually factored to help us convince ourselves of that. Now here's why I showed you that. What about this? I don't need the 2 on that, sorry. So you could still do this, say that's infinity minus this is headed to infinity, right? Which one dominates?
The x squared, root square root of x.
The square root. So you're comfortable with the idea that the square root of x is bigger than the cube root of x for big x's. I would agree. I would agree that that's true. I mean, if you're comfortable with that, you can just say the answer is infinity here. But I want to show you how we can do it using this, the same idea of factoring. All right, so I don't know how many of you have ever tried this before, but we can factor this. What I'm going to do is turn this into x to the half minus x to the 1/3. That's what those mean, right? That's what those mean. Now watch this. This is I'm showing this to you because if you haven't seen this, this is pretty cool. So now what I'm going to do is I'm going to write those fractions with common denominators. In other words, I'm going to have common denominator between these two numbers is 6. So I'm going to rewrite the first one as x to the 3/6. And the other one I'm going to rewrite as x to the 2/6. It's the same fractions, right? 1/3 is 2/6 and 1/2 is 3/6. Agree? Now the tricky, the clever part. Now what I realize is that they both have something in common. They both have an x to the 2/6. So I pull out an x to the 2/6. And then, I don't know, what would we need here? To multiply, what would we need to multiply this by to get back this?
Maybe
It'd have to be x to what power though? You're going to add them, right? You're going to add the powers?
1/6.
1/6. Good. And then minus, now what do you need here?
1, wouldn't it be?
1, right? So this is really the cube root of x, okay? because that's what that is, right? X to the 2 6 is the same as x to the 1/3. That's really the cube root of x. And this is the 6th root of x minus 1. And now that you've got it factored, you can verify that that goes to infinity times, and then this right here is infinity minus 1, which goes to infinity. And so when you multiply the two, you get infinity. So look, I'm showing you that because I want you to see that in calculus, we can factor things like this, all right? I just wanted you to see that factoring of this, just to make sure you've been exposed to it at some point. Okay. One more? Yeah, one more. Limit x goes to negative infinity. First time we've seen this. And then let's go 1 plus x to the 6th over x to the 3rd plus 1. All right, so we're taking an infinitely large number that's negative and raising it to the 6th power. What's that going to give me?
Infinity.
Positive, right? Huge positive number. And then add 1, still going to be huge and positive. Over, now I'm taking x and raising it to the 3rd, right? So I'm taking a huge negative number and cubing it, which will be
negative
what?
infinity.
Negative infinity. And then we add 1. Still
No.
negative infinity.
So a
right?
huge
Still
negative infinity.
Now we've never had positive over negative, but it doesn't matter. We do the same idea, okay? Same principle. And that is we will look at the highest power and we will try and get rid of it. So we do 1 over x cubed here, 1 over x cubed here, distribute through. And we should get limit x goes to negative infinity. Okay, distribute there, we get 1 over x cubed plus x, this should just be x cubed. And then over 1 plus 1 over x cubed. So distribute top and bottom. We all good with that? Anything that has fixed over x is going to go to 0. Doesn't matter that it's going to be negative on bottom, right? It's still headed to 0, just it's going to go to 0 through really small negative numbers instead. But it's still headed to 0. And the denominator is headed to 1. But what about the numerator? Where's it headed?
Negative infinity.
Negative infinity. Because we're taking a negative number, we're plugging in there, we're cubing it, it's going to become negative infinity. Negative infinity over 1 is negative infinity. But you cannot just look at infinity over negative infinity and tell me the answer is negative infinity. You can't do that. You have to go through this analysis. All right, so that concludes the first half of 1.6. So 1.6 has 2 different concepts in it. The first concept that we are looking at in 1.6 is this idea that we're taking limits and we're letting the x go to infinity or negative infinity. All right, that's the concept we were just looking at. Let me open up the notes for today. Hold on. If I can find. Where is it? Chapter 2. Oh no, chapter 1. What the heck? Chapter 1. Okay, limits involving, so we just did what are called infinite limits. Where is it? Sorry. There we go. Limits at infinity. There we go. So I did this section a little bit different than the notes. I decided to do the second half first, and then I'm gonna go back and do the first half of the notes. So everything we've been doing has been what are called limits at infinity. That means we're letting x become infinite or negative infinity, right? Those are called limits at infinity. Now we're going to talk about something called infinite limits. Not limits at infinity, infinite limits. So I'm going to motivate this with an example. So if I ask you right now, what is the limit as x approaches infinity of 1 over x squared? Everyone here is going to tell me the answer is what?
0.
Zero, right? Because it's fixed over infinity, right? Nothing to do. Fixed over infinity, that heads to 0. Well, let me ask you a different question. What is the limit as x approaches 0 of this function? That's a different question now, right? Here I'm saying let x become infinitely big. Okay, fixed over infinity is going to become 0. We're done, nothing to do, right? Here, though, this is a little different. Because what's happening here is on top, we have a fixed number, right? But where's the denominator headed? Not infinity, but what? 0, right? 0. So think about
Would
what's
that be
happening.
infinity?
What's that?
Wouldn't that be infinity?
It will depend, but generally speaking, you're on the right trail. So like imagine you have a number that's fixed, right? And you start dividing it by numbers that are getting smaller. Let's try it. Let's just fix a number. I'll just pick a number, 5, okay? Let's divide that by a small number, 1/10, right? Well, to do this, if you do 5 divided by 1/10, you flip the bottom fraction over, it becomes a 10, and this is 50, isn't it?
Yeah, the smaller you get, the bigger the number is going to get.
That's right. If I keep the 5 fixed, but make the denominator smaller, I'm going to keep getting bigger answers. 5 divided by 1,000 is 5,000. So the smaller this denominator gets, right? Oops, sorry, that last one was wrong. I wrote it down wrong. It was supposed to be 5 over 1 over 1,000, right? You can see those blue denominators are getting smaller, right? And smaller the denominators are, right? So if your numerator is fixed and your denominator gets smaller, the answers are getting bigger, right? Bigger, bigger. It's the opposite of what we just had, right? When we had fixed over infinity, well, that went to 0, right? Because your numerator is getting fixed, your denominator is blowing up, the ratio gets tiny. Here it's the opposite. Your numerator is fixed, denominator gets small, ratio gets big, okay? Ratio gets big. The problem is that we actually run into an issue with the sign, because is it getting really big like positive infinity, or is it getting really big like negative infinity? Those are two different things, right? So we have to pay a little more attention to it, which is why on your formulas, right, this little limit summary, we have now talked about, let me see, I'm gonna highlight everything that we've done, okay? We have talked about 0 over 0, we have talked about infinity over infinity. We actually just talked about infinity minus infinity, right? Because I just factored, remember I was factoring just a second ago? And we have talked about fixed over infinity being 0. Those we've covered. The top right one shouldn't require any thought from us. If we take a limit and the top heads to 0 and the bottom goes to a fixed number, our answer is 0. So everything in yellow we should be somewhat comfortable with. What I'm now asking you to think about are these 4 scenarios. What if we have a limit where the top is fixed but positive and the bottom is heading to 0 through positive numbers? Then a positive divided by a positive should be an infinitely big number, but positive. If they're both negatives, then our answer should still be positive infinity. If one of them is positive and the other one's negative, then our ratio should be really big but negative. That's just using the property of signs, right? Like signs divide to be positive and unlike signs divide to be negative. So let's get back to this question that I put up here. What's happening as we head to 0? We are, for the first time ever, we are getting this form, right? That's the form of the limit we're getting. Anytime we see this form, there are 3 possible answers, okay? So this should now become this thing that just goes through your mind. As soon as you see fixed over 0, you should be thinking, my 3 possible answers are this. It's either infinity, or it's negative infinity, or there's a possibility that the limit does not exist. That's it. Those are the only 3 outcomes possible. So how are we going to determine what's going on here? All right, how are we going to do it? You ready? You ready to see how to do this? So I'm going into this. I already know it's fixed over 0. I know there are 3 possible outcomes. So what I'm going to do is see if I can't investigate and determine which of these 3 it is. And the way I'm going to do it is going to seem kind of like primitive, but it's very effective. All I'm going to do is draw a number line. And I'm going to put where I'm headed right here, 0. And now I'm not saying which side to come in, right? I'm not saying which side to come in. I don't have a plus or a minus on the 0, so I have to check both directions. So if I come in from the left, a number that would be to the left of 0 would be something like negative 0.0001. If I were to take that number and plug it in right here, I would then square it, wouldn't I? And that would turn it into a positive. And so I know my denominator is always going to be positive, isn't it? Because of the square. And my numerator is also always positive because it's a 1. So I can now conclude that the top is fixed and positive, right? It's fixed and positive because it's a 1. And the denominator is also headed to 0, but positive because there's a squared on it. And that would happen even if I come in from the other side, right? 0.000 whatever 1. Doesn't matter because when I square it, it's positive. So regardless of which side I come in from, the top's always positive, the bottom is always positive, and I already know that it becomes infinite. It's just a question of was it positive or negative? Well, it's got to be positive then.
So if this was 1 over x cubed, this would be something different.
Let's do that. Let's do that. Okay, let's do 1 over x cubed because it's not going to give you the same answer. So let's do limit x approaches 0. This time I'm going to come in from one side at a time of 1 over x cubed. All right, so I start the problem out. I sit here and I look at it. I go, okay, the top is fixed, right? Top is fixed. I'm even going to add on there that it's positive. It's a fixed positive number. Now the denominator is headed to 0. But I don't know if it's headed to 0 through positive or negative numbers yet. I need to actually do an investigation. Does everyone understand that? I don't know if that's positive or negative yet. And don't think just because it's cubed, it's going to be negative. You have to actually analyze this. So which side of 0 are we approaching on?
Left.
Left. Okay, so I'm coming in this way. So I have to pick a number here, which is a negative number, negative 0.0001. The important thing is that it's negative, right? And what would happen if I took a negative number and cubed it?
Negative.
It
Stays negative. So that means this will be a negative on the bottom, right? And so I have a positive over negative, and therefore my answer would be what?
Negative infinity.
Negative infinity. And there's no other work to do, okay?
So just a quick question, if that one was asking for the limit, not, but didn't specify direction, it would be a D&E, right?
Yeah, so I was going to get to that. Let me show you. Let's do the same problem coming in from the right instead of the left, right? So if we do that, the top is still fixed. and positive. The denominator is headed to 0, but I'm not quite sure if it's positive or negative yet, right? I don't know. I know it's headed to 0, but I just don't know if it's positive or negative. So I draw a little number line. Here's 0. I'm coming in from the right this time. So something like 0.0001. That's a positive number, right? And I'm cubing it, which means it's going to stay positive. So I know this is positive. And a positive divided by positive would be positive. So this is headed to positive infinity.
And so since from the left it's negative infinity and the right it's positive infinity or difference, so that's going to be a D and E.
Yep. So now if I ask you this question, right? And I don't put plus or minus, you have to check both sides, which we've already done, right? So if you check from the left, we got negative infinity, and from the right, we got positive infinity. And that means these don't match, right? These aren't the same. And so this limit would not exist. So yes, very good. We could graph it to confirm it. I mean, if you just go and graph this function, 1 over x cubed. There's the graph. So you can see that as we come in from the left, we're headed down to negative infinity down there, right? Way down there. And then if we come in from the right, it's headed to positive infinity. There we go. And that's what we got. Any questions? These are about to get a little more challenging. So any questions on the idea here? If you get fixed over 0, it's just a matter of analyzing things and figuring out like what's happening. It's very different, right? Fixed over 0 is very different than fixed over infinity. Fixed over infinity is 0. We don't have to think about it anymore, right? But fixed over 0 you're gonna have some work. Okay, so let me see here. I'm gonna give you this one and I'm gonna let you work on it. Okay, I'm gonna see how you do with this one. Limit x approaches -5 from the left of x plus 4 over x plus 5. All right. See, we're going to do breakouts. We're not going to take a whole lot of time, but we're going to do breakouts just to see if y'all can talk together on this. There you go. See what you can do in about 7 or 8 minutes together. Maddie, I still have this hat. It's been through something now. Still my favorite hat though. All right, everyone's back. All right, who wants to walk me through this or walk us through this?
I can.
Okay, go ahead.
So it's looking like if you apply a -5 into it, you
Okay,
get a -1/0. So that obviously doesn't work. But if we draw our number line, which that's a negative fixed over 0. We draw a number line, we're approaching -5 from the left. So that will be a larger than 5 negative number,
like what?
like -5.01.
Okay, good. So sometimes I see a mistake there and students will put -4.999 or something like that.
Exactly.
Don't worry, I did that.
Yeah,
I was
yeah,
sitting there and I started trying to talk about it with my people in my group, and I completely went backwards as I was trying to talk about it and did it wrong.
that's why I gave you that problem. Just specifically to make sure that you don't make that mistake on a test.
Well, what's funny is it was after I did it right in my head and then started trying to talk about it and went, wait, no, it did it wrong.
The other side, yeah.
So then what we have is we have technically a very small negative number as we were approaching 0, as we were approaching -5.
Yes. Is everyone clear on that? Because we're coming in from the left of -5, like -5.0001, when we plug it in here and add 5, it's going to be a really small negative number. All we care about is the sign. We already know it's going to 0, but it's going to be a negative number, which means the bottom is also negative, right? We knew the top was fixed. It was -1. We knew it was negative. So now we know we have a negative over negative. And so the answer? Positive.
Yeah, positive.
Right? There we go. That's it. That's how it works. Okay, let's do another one. Any questions on that? Okay, let me think real quick how I want to do this. Yeah, let's do limit as x approaches 0 from the left of x squared. Hold on. No. X plus 1 cosecant of x. All right, have not seen one of these yet. So let's look at this. X is headed to 0, right? So where is this headed?
1.
1, right? That's headed to 1 times, okay, cosecant of x. Well, I'm not expecting that you're going to remember what cosecant looks like.
Yes, please explain what that is. I don't remember it.
Yeah, so instead, why don't we look at this problem this way? Because this I would expect you to be comfortable with. This is the same as x plus 1 over sine x. Because cosecant of x is 1 over sine, isn't it? And so I could just put the sign underneath the x plus 1 like this. And now I know the numerator is headed to 1, which is obviously a fixed positive number. And the denominator is headed to, well, sine of 0, right? Sine of 0 is 0. So it's headed to 0. But we're not quite sure if it's headed through positive or negative numbers. Agreed? So I'm going to draw a number line. It's going to be a little tricky. We're going to plug 0 in, or we're going to put 0 in the number line. We're going to approach it from the left. So a number like -0.0001, something like that, right? but we're plugging it into the sine function, right? Like in the previous problem, we were just plugging it in right here and just adding 5. And I think it was easy to see that this will give you a small negative number. But when we plug this number into sine, it's not as obvious. So what would help us here is if we knew what sine looked like. And we all know the sine function looks like this, right? And we're approaching 0 from the left, which means I need to draw the sine function backwards a little bit and approach 0 from the left. So here's 0 on the x-axis. I'm approaching from the left. I know it's headed to 0, but what about the numbers here? What are the values of the sine function here?
Yeah, they're going to be very small negative numbers.
Small negative numbers, because I'm coming in from the bottom of the x-axis. So these are little small negative numbers, which means that this, I know I'm approaching 0 through negative numbers. So I have a positive divided by a negative. So that should give me negative infinity.
Or could we like plug in, you know, sine 0.000 negative 0.001 or something like that? Or are we supposed to actually memorize? I know you like the word memorize, but like kind of remember what the sine function looks like from the left side? Or?
I would say that at this point, you should know what sine and cosine look like from the left and right. Yeah. I mean, could you just go to your calculator and do that? Yeah, you could. But I'm just saying, like, for your own, like, just what's expected later and now is that everyone here knows what sine and cosine looks like. Maybe not what cosecant looks like. All cosecant is you just draw vertical asymptotes at all the x-intercepts. And then you just draw those little U's that went like that. But that I'm not expecting that, but I'm expecting for you to know what sine looks like. So this is cosecant x.
I've forgotten what cosecant looked like. It looked stupid.
Yeah, it looks like a bunch of little parabolas. Okay, that is it for this section. All right. Now, again, this had two different parts to it, this section, right? We had limits at infinity, which meant we were doing limits where x was going to either positive or negative infinity. And then we had infinite limits, where when we did the limit, right, it didn't matter what the limit was, but we were getting something like fixed over 0, and that was either going to be infinity, negative infinity, or does not exist. Those are two different types of limits, limits at infinity and infinite limits. What we studied last time and the first part of today, this is how we discover what the horizontal asymptotes of something are. So that's college algebra, right? If you want to know what's happening at the end of the function, right? If you want to know the end behavior of a function, then you're going to be looking at these limits. You're going to take the limit as x goes to positive and negative infinity, and it will tell you what's happening at the ends. What do you think this has to do with? Not the horizontal asymptotes, but what? Look at the graphs. The verticals, right? This is where we have vertical asymptotes. So we kind of snuck it in here, but that's what we're really looking at, is another way to find horizontal and vertical asymptotes of functions. So if you ever want to know what the horizontal asymptotes of a function are, you take these limits. You let x go to infinity and negative infinity. If you want to know where you have vertical asymptotes, you figure out all the places where you get fixed over 0 when you do limits. And those will correspond to your horizontal and vertical asymptotes respectively. And that's for any function, not just the polynomials and rationals that you studied in college algebra. This is for all functions out there. All right, we are done with this. We've got about 11 minutes. So I think I can talk about the last topic. We are done with 1.6. We are going to go to 1.5 now. And remember, I told you we're going to skip 1.5, come back to it. So we have this idea of continuity, all right? Continuity. So continuity is a very important property when it comes to calculus. The idea is very simple, all right? Continuity just means that you can draw the function without picking up your pencil. That's pretty much what it means for a function to be continuous. So if I graph a function and I can do it in a way that I never have to pick up my pencil, then that would be continuous. If I have something that looks like this, this would be continuous everywhere except right here. Let's say that that's the value A. Because if I were drawing this, I would actually have to pick up my pencil to go over that hole and then continue drawing. So this would not be continuous at x equals A. This one would be continuous everywhere.
Sir, would it be like that for every time there's a hole in the graph?
Anytime you have a hole, you now have you have what we call a discontinuity at that, whatever at that point is. Anytime you have a hole, that's a discontinuity. All right.
Vertical asymptote as well.
Vertical asymptote would be a discontinuity. What else? So this is called a hole. This would be a hole. Someone said if you had a vertical asymptote, that would be a discontinuity.
Would a horizontal one be?
No, not necessarily, because you could still draw with your pencil, right? You just keep drawing as you go out forever. But if I try and draw this, I have to pick up my pencil to draw the other side. So a vertical asymptote, put VA for vertical asymptote. So if we have a hole, we're not continuous there, right? If we have a vertical asymptote, let's say this is A, this would not be continuous at x equals A. Can anyone think of another way you could draw a function where you would have a discontinuity that's not one of these two?
I guess when it's not a limit.
How do you mean?
I don't know how to describe it, but if you have one going in one direction and then it's just not a limit.
Okay, so how about, I think I understand what you're saying. Let's say we go to some point A, and then like from the left, you have it coming in here, but then from the right, it's coming in somewhere else, like that.
Yes, yes, sir.
Right. This would be a jump or a break in the graph, right? Anytime we have a break or a jump, that would not, I could not draw that without picking up my pencil. Now, could I, if I filled in this dot right here, solid, doesn't make any difference? We still have to pick up our pencil? We still have to pick up our pencil, right? I can have the dot there, or I can take the dot away, or I can put the dot down here, still pick up my pencil, or take it away. I could put the dot up here, right? Take it away. It doesn't matter. It still have to pick up my pencil. Y'all agree? So when it comes to this idea of continuity, we have this idea that a function that you can draw without picking up your pencil would be continuous everywhere. If you have a hole somewhere, it's not continuous at that hole. If you have a vertical asymptote, it's not continuous at that value A. If you have a jump or a break, it's going to be not continuous there, right? So is there a way we can define what continuity means in a different manner that I'm not sitting here telling you draw it without picking up your pencil, in a more mathematical, precise way? Can I define continuity? So let me see if I can get you to understand this. So let's say I'm going to look at a function, okay? And let's just go to some value A. And I want it to be continuous at x equals a. Well, then I can't have a hole, right? I can't have a hole, right? So I've got to have some value there. I've got to have some dot, right? And I can't have a vertical asymptote. And I can't have what Daniel said, I can't have limits be different from both sides, right? So from the left, I'd have to go into that point from the left and the right, wouldn't I? So I'd have to come in from the left and from the right and not have a hole, so it would have to be filled in right there where they come together, right? Does that make sense? So here's another way I could write this. Let's act like this value of this function right here. Let's call that, I don't know, C, okay? That's how high that point is. If I'm going to tell you that you're continuous at that point, if I want to say, hey, look, you're continuous at this point, x equals a, here's what would have to happen. We would need the limit as x approaches a from both sides of this function. We would need it to be equal to c, wouldn't we? We would need that as you come in from the left and right, you're headed to c. Agreed? We would also need the function's value at a to be c. What does this do? What does f of a being c mean?
Means there's no hole.
There's no hole.
Yeah, it's
And not only
continuous.
is there no hole, see, you have to be careful because I'm not just saying there's no hole, because this would still not be continuous, right? Not only do I need there to be the function to be defined here, right? I need the function to actually be defined. I need to actually fill that hole in right there, which means that I need that value of the function to be equivalent or equal to that same value that the limit's equal to. So as you come in from both sides, you're headed to the same point, and when you get to that point, it's actually filled in right there. That makes sense? And if both of these are equal to c, then can't I just get rid of that and just put these two equal to one another? And just say this, the limit as x approaches a of this function must be equal to the function's value at a. If this is true, right, if that right there is true, then what we have is continuity at x equals a. If any of this is not satisfied, then you're going to have to pick up your pencil. Think about that. If this limit on the left side, if the limit doesn't exist, then you're not going to the same place. So you need the left side to exist. If f of a is undefined, then you have a hole. So we need that hole to be filled in. But by putting them equal to one another, that forces the function to come into the same point. And that's the very, very simple, precise way of saying a function is continuous at a. So here's basically everything I just said. Is this function continuous at 2? No, it has a hole, right? I mean, it's not continuous at 2. Is it continuous at 3?
Yes.
Yes. Let's see why. Because if we go to 3, right, there it's defined. And as we come in from the left and we come in from the right, they're both headed to that blue dot, and the blue dot is right there on the graph, right? Everything comes together. So this would be continuous at 3, but not continuous at 2. Would it be continuous at 1?
Yes.
Yes. Continuous at -1?
Yep.
Yeah. In fact, it would be continuous everywhere here, wouldn't it? Only that point. That's the only point. That's the only point that you could ever pick, 2, that you would fail to have continuity. Still not continuous, right? Still not continuous. Now you're continuous, right? Now this is a continuous function at 2. In fact, this one is continuous everywhere. The 3 types of discontinuities you can have. I've already discussed. Anytime we have a jump, if we have a vertical asymptote, this is called an infinite discontinuity because like your function is either going to infinity or negative infinity. That would be discontinuity. And this one is called removable. So if you have a hole, we call that a removable discontinuity. The reason we call it removable is because there would be an easy fix if I wanted to fix it. If I wanted to fix this and make it continuous, all I'd have to do is define the function there. If I did that simple fix, it would be continuous, wouldn't it? So it's removable in the sense that it would be easy to remove that problem. The other two, you can't remove this discontinuity easily without changing the whole shape of the graph. Same with this, you can't remove this unless you somehow brought them together, but that would change the whole spirit of what the function's doing. Now, we have an addition, oh, I'm out of time. Okay, so we will talk more about continuity next time. Don't worry about any homework from this section. All you need to focus on is the homework from 1.6. All these problems here from 1.6, you should now go after. I'm going to send you all a review for the exam, which takes place a week from Thursday. I'm going to send this review to you, and this review is going to be counted as 2 quiz grades. All right. I will provide you the key to the review, but I'll provide you the key probably on, I don't know, Tuesday after class. So next Tuesday after class, I'll provide you the key. But that means that it's due Tuesday before class of next week. All right, I'll put this in the email. 2 quiz grades over that review. Everything will be due on Tuesday before class, and then I'll provide you the key so you can study a little bit more and know what you were doing right and wrong. Okay?
We get it today, right?
I'm going to send it right after class.
Thank you.
Okay, anything else? I saw some chat here. I haven't looked at chat all day, so.
I have a question.
Yes.
So in this folder,